everybody. I hope everyone's having a wonderful day. So last day I introduced you to Multiway Search Trees, a generalization of a binary search tree. Now remember, in a multi-way search tree, we had it where we had, instead of just having two children for each one of our internal nodes, we had it where now we have at most D children. So it could be at least 2 or at most D for an internal node. We still have leaves just like placeholders, and we started talking about how we can do some of our standard operations used over a general multi-way search tree. So we talked about how we can get, we can put, we can find the smallest, and now we want to talk about a couple others here. We're going to first talk about the successor. Now, in a binary search tree, when we computed the successor, what did we do? So what I did was I tried to find that one with the given key. And then what did I do? I went to its right child and I went and used smallest, right? If that existed. If it didn't exist, what did I do? I followed up my parent references until what happened? Until I found a specific key that was bigger than the one I'm looking at. Now in a binary search tree, it's really easy to guess that. In a multi-way search tree, it's really not that much different. You just have a new case because we now have multiple records in a node. So let me illustrate this. So if I wanted to get the successor of 14, what would I do? Well, I would go down its child associated with this. Remember, there's the first one is always this one, which is associated with that infinity element, the sentinel key. This one is associated with this child. This is associated with that child. Wherever the child is always the bigger than itself. So 14, the child associated with 14 is always going to have keys that are going to be bigger than itself. Just like 30 contains in its child all the ones that are bigger than 30. So what's the successor of 14? Well, what I do is I notice, hey, look, I have a child. So what do? I just go here and then I compute smallest. Is that simple? So that's exactly what we did. And this is very often what we did when we did removals, right? Which is going to be relevant later. So there seems to be 3 cases that we have. So the first one you're familiar with. So get the immediate child whose subtree has keys greater than k. So obviously remember, you still have to do get, right? So you do get, then this. Then we have this. So remember, this is just, so if I give you some node P, it'll be P dot child sub I if K is equal to keys sub I. So assuming that's an internal node, you should be able to do this. Then use smallest. So you can use what I described last day to find the successor in this fashion. So that's the trivial case. Now, if this does not happen, if one does not happen, so if one doesn't happen, what do we have to do next? So I want to point my finger at something else. Say for example, if we want the successor of 1. Well, I could find 1 and then I get this is P, so this node is P. I have no immediate child below me, so where should it be located? It should be located it's the next record over, right? Then if they're there is a record at position I plus 1, so 1 higher, in P, it is the successor. The marker's a little funky. I'm going to grab a different one. These aren't my fun scented ones. Let me just throw that. There it goes. And then obviously, it should be worth noting that no successor exists if this node has no parent. So that's case number 2. You're going to find obviously that this statement here is just as true wherever. Because now, after this point, what do? This is going to fall back into our case where we did in the binary search tree, where we work up the tree. If 1 or 2 does not happen, if neither happens, travel up the tree by following ancestors. So you just follow the parent references. To find the smallest key bigger than k. So no successor obviously exists if this fails. So let me just remark that. No successor exists if this fails. So just to illustrate my point, if I want to get the successor of 50, I have no child immediate to 50, but I have no record to my right. So what I do is I work my way up the tree. Then I see nothing that's bigger than 50, so I work up the tree, but that's the root, so I even find it. So these are your 3 cases in the successor. So you just use get to find a node P where K would be located, and then you consider these 3 cases. Okay, so that brings me to talk about the time complexity for this. Let's do it over here. So what's the time complexity here? I'm not going to write it out too fancy because we've done this many times. Finding node P, the one I mentioned before where you use get, it takes big O of h log d time, right? That's what we established last day. So if case 1 happens, how long does that take? If this happens, how long does this take? Well, I just compute the smallest, right? But how long does this take? This takes big O of h. Let me just write them off to the side here. So this takes big O of h. Case 2, if that doesn't happen, what happens if otherwise? Okay, well, if I know I don't have an immediate child, say right here, then I know it's immediately to my right, if it exists, right? This should take constant time. That takes constant time to do. How about 3? Does everybody see that? So it's basically a modification of step 2. So case number 2 here. all I'm doing is I go up the ancestor, I do case 2. But to do case 2, it requires me to use binary search to find the position I. Okay? And that takes h log d because I have to do this for each level of the tree, and I perform this binary search procedure. So that's successor. So how does removing work? It's just like a binary search tree, believe it or not. So, like I said, put was really straightforward. Once we had get, it's going to be very much the same idea here. So we're just going to find. So you're just going to find record KO, remove KO, and replace it with its successor, if needed. Then, of course, you have to... Now, remember, when you replace the successor, did we just, leave the successor just sticking around in the tree? No, right? We have to still delete the successor from where it originally was. Then, delete relevant data in that node as applicable. As applicable. So, I should be very clear that when you do this, we might completely destroy the structure of the tree because I haven't given you any conditions for which this is okay to do and when it isn't okay to do on a given node. So let's do an example and you'll see what I mean. So I perform, let's try doing a remove on 42. So let's try removing 42. So I remove, I give you R, and I pass along 42. So what do I do? '42 is right there, right? So I just use get, I find this node, and I find the record. Then what I do is I just delete it, right? What kind of case was this? Remember, I had two cases. I had case 1, where I immediately knew that both my children, or all of, now in this case it's all my children, if all my children are leaf nodes, I can just straight up delete this, right? So the analogous case 1 exists here, except instead of just saying both, you'll say all. So that's how you remove 42. It's straightforward, because all of its children are leaf nodes. How about if I want to remove 11? Let's try removing 11. So, if I remove 11, where is it? It's right there. So what do I do? What did I do before? Now remember, I have at least one leaf node, but at the same time, I most definitely don't have all of my children with leaf nodes. What did I do before? I had a second case in my binary search tree algorithm, right? What do? I replace 11 with its successor, which I already showed you how you do. But remember, in this case, it's always going to perform the first case because it always has at least one child. Did everybody see that? In fact, in particular, it has it has an immediate child because it exists. So it's either going to find the immediate one or it's going to find the one that's just right beside it. So if it finds the one right beside it, we don't have to do anything, right? But it's most definitely not going to be up here because I know there's at least one non-leaf node below here, right? Does everybody get that? So I replace 11 with 12. Then I have to delete the successor from here. So that means I need to get rid of this leaf node right here. And now I'm done my removal. Does everybody see that? So all I do is, if I have an internal node, I replace it with its successor, then I delete the record for which the successor did exist. Just like I did in the binary search tree, just now you need to make sure you erase the appropriate leaf node. So in our case, it's always the one just before it. So remember, I associate each one with the one that comes right after it. you delete the one that comes just before it. So that would be the position just to its left. Okay? So just be very careful. That's what this as applicable business means. So when I perform this, what happens? I have to update this data structure in here. How long does that take? I'll let you think about it. So compute the successor. Once we have that, we can do our removals. And we have all these cases here. But remember, we have one of two possibilities. Either I have all my children being leaf nodes, which I just delete it right out. Otherwise, I could just simply just delete the record if there's the successor already exists in the node. How do I know it exists? Remember, there's at least one child, right? Just like over here, if I attempted to delete 32 before I had 42 here, I would know right away that, okay, well, it's blatantly obvious that if I tried to delete 32, I know that there's going to be a successor below it because there exists at least one other node in another record here. And it has, in fact, an immediate child below it. If this didn't exist, then I would just simply get rid of this entirely, right? So before we get to the time complexity, I just wrote up here what exactly we need to do for our removal. It's very straightforward. Like in our example, I just simply delete the successor. So I replace the node with its successor if I need to. So if it's an internal node with at least one non-leaf child, then I need to do something like that. And it's not that much different. So let's talk about the time complexity. So let me write this down. So searching. So first we have to perform a get operation, right? Whatever modification we need to make. Search for the record. The train's getting very excited again. With key K, takes, how long? It was h log d, right? It was h log d. Then, we compute the smallest sometimes. Then, computing smallest. Then computing smallest takes big O of h time. Then what? So remember, just computing the successor in general is h log d, so this isn't really terribly interesting at this point. Because naturally I'm just computing the successor if I need to. So removing, that's supposed to say removing any data and deletion, because it might be possible I have to delete more leaf nodes. I might have to delete possibly 2. Just say if I end up with just a node with a single record in it, if I had to delete that, I would have to delete 2 leaf nodes. Otherwise I'd usually delete 1. The deletion of possibly 2 nodes may occur. How long does this take? So if I want to update those arrays that I have, that takes big O of d. Deleting these 2 constant number of leaves, constant time. So this is going to take me big O of d. Therefore, how long should remove take? Remove takes big O of d for the removal and any bookkeeping we need to do with the tree. D plus h log d. Remember, h log d, that's associated with me getting the node, and also the successor. Okay, so we've talked about all the main operations we need for a multi-way search tree. I'm going to get more specific, by the way. So you've seen that I talked about these really general approaches for inserting, removing, and so on. But the big thing I want you to observe is that there wasn't really much structure that was at play. D could have changed, like the order of the tree could change quite dramatically. Likewise, the example of removals, it's very possible for me to remove all the records from a node and it's just sitting there with no records in it, right? That's very possible. I've really not really sat anything down and said, hey, look, if this happens in your tree, then do this other thing. We want to make sure we maintain some specialized structure so we can maintain something we can use that has properties that maintain an efficient structure that we can use for all these standard operations. Does everybody get that? So we're going to first talk about 2-4 trees. So this is a specific kind of multi-way search tree. You're going to find we're going to get more and more general, and by the end of this, you're going to get a very broad structure. So we're going to consider a particular kind of multi-way search tree called a 2-4 tree. Sometimes it's called a 2-4 tree like this with a hyphen. Sometimes people call it a 2-3-4 tree. And some literally write 2-4 tree without a hyphen. So just be aware that other people speak of this data structure in a somewhat different way. So here's the definition. So it's a multi-way search tree. It's a multi-way search tree that satisfies the following two properties. So we have two properties. So just like when we did our AVL trees, we had a very specific property we wanted to maintain at all times. We're going to do the same thing for our 2-4 trees. There's going to be two properties we want to make sure we maintain. And very interestingly, these are the same two I brought up. The concept of a node that gets really fat, and also the notion that the nodes can all of a sudden just have no records in them. Likewise, this issue where we had this ambiguity between, okay, well, if this one has no records in it versus this other one, and the idea that these leaves, like sometimes there are nodes with literally no, there is some nodes with no internal nodes as children, where they're all leaves. Some will have that. So I want to kind of remedy these two properties in our trees, and we'll see that we actually get some really nice properties as a result. If we stop assuming that our tree always satisfies these two things. So each internal node has at most 4 children. So it has at most 4 children. And the other one is called the depth property. So we have the size property and the depth property. So every leaf node has the same depth. So if I looked at my tree, all the leaf nodes would be on the same level of the tree. So when you think about a 2-4 tree, the nodes are only going to look like the following. So in our tree, you only have nodes that look like this. So you have a 2 node, a 3 node, and a 4 node. So the nodes in this tree will look only like one of the 3, where any one of these could potentially be an internal node. However, all of the leaf nodes are going to be on the same level. Let me show you an example of what I mean. So I have 11, 21, and 28 in the root. I'm going to have 5 and 7 as records in that node. I'm going to have 18 in the second child. The third child is going to be 23. That's it's an adult there. And the last of them, the fourth child, is going to have 30, 36, and 42 in it. And then all of these are going to have leaf children. So this is a 2-4 tree. Notice that all the leaves are on the same level. So they all line up like this. And it has the size property. So they have at least 2 and at most 4 children. They already see that. So this is true in this tree. And it maintains the multi-way search tree properties I described before. What's the order of this tree, by the way? What's the order? What's D for the tree? It's 4, right? So the order is D equal 4. So you want to think of D like a constant now, like I alluded to previously. Furthermore, I also want you to think about this, is that there might be a more general pattern that's going on. You're going to see some things reminiscent from earlier parts of this course when we started talking about binary search trees. Furthermore, I'm going to sometimes use D like it's some variable. It's because it can be, but in the context of the 2-4 tree, it is fixed and a constant. It is 4. The reason why is because later on I'm going to show you a more generalized structure where D is no longer 4. Okay? So just keep that in mind. So right now we're just going to focus on the 2-4 trees where the order is 4. So here's the claim. So my order is going to be at most 4. And here's my claim I want to prove for you. So any 2-4 tree with n records has height big O of log n. So we're going to prove this. I'm going to use an argument that's quite similar to one that we used before. So here's the proof. So I'm going to let H be the height. Remember, I have to consider any 2-4 tree, right? The height of a 2-4 tree. I'm going to give it a name. I'm going to call it T with n items. Now I want you to look at this tree that I have up here. This is actually a simpler structure for the tree. Say if I want to maximize the amount of height I have with n records, what would the tree actually look like? Would it be all wide and bushy like this tree is? Like, is it bushy like this? Or if I want to make the tree's height as big as possible, what would I do? I would try to put those records in as many nodes as possible to fill out this tree, right? I don't want it bushy. I want it to be as tall as possible. What would that look like? It would look a lot like a binary search tree, right? So observe that every internal node is at least a 2 node, right? Has at least 2 children. It's at least a 2 node. Then T has at least 2 to the power of I items at level I is equal to 0, 1, all the way up to h minus 1. This should look very familiar to you. I'm doing something that you may recall from when we did our proof with heaps. So I'm going to consider all the ones I have. So remember, I'm trying to maximize the height. So what do? Is I try to put these into as many nodes as possible to make the height as big as possible. So how do I do that? Well, I think of it like a binary search tree. Then T has at least 2 items at each level I. So that's for each one of those levels. But what's true about the depth property? So first, am I okay with this? Because this should satisfy the size property, right? How about the depth property? What can I use with that? Well, okay, I know that all of those levels, there's going to be records, right? But what level is this? This is the last level of the tree. Are there any items there? No, right? And no items at level H by the depth property. So, what can we say? Well, what does that mean? Well, I have something below that is actually going to operate like a bound in relation to n, the number of records. So, n is greater than or equal to 2 to the power of 0 plus 2 to the power of 1 plus 2 squared plus so on up to 2 to the power of h minus 1. Remember, those are all the ones in my tree. Remember, I want to make this height as big as I can, while at the same time I'm bounding the number of records from below. You're going to see why. But what is this? This is just a geometric series, and I can simplify this a little bit. I can get 2 to the h minus 1. Sorry, 2 to the h. Remember, it always goes up by 1 here. Minus 1. Which that means, so I have now that n is greater or equal to 2 to the h minus 1. So what does that mean if I rearrange this? It means that 2 to the power of h is less than or equal to n plus 1 by adding 1 to both sides of my inequality. Does everybody see that? Now what was the trick I normally use here? Now I'm going to exponent. So I'm going to take logarithms, right? I'm going to take logarithms to both sides. Take logarithms to both sides of the inequality. To both sides of the inequality. It follows that. Now, okay, so if I take logarithms to both sides, what do I get? Well, I get log base 2 of 2 to the power of h, less or equal to log base 2 of n plus 1 altogether. I can use the power rule of logarithms to bring the h down in front of the logarithm, and I end up with log base 2 of 2, which is just 1. So I end up with h is less than or equal to log base 2 of n plus 1. Therefore, h is big O of log n. And we're done. That's the end of the proof. Is that cool? So now I want you to remember, what are the running times for searching in a multi-way search tree? What was my get algorithm? How long did that take? Well, it took, how long? It took h log d, right? If my memory serves me correctly. What's the obvious corollary to this claim? it means that since D is equal to 4, so I'm just going to assume D is like some sort of bound for my tree. So the order, I want to maintain this order of 4, but in reality the tree might have actually an order that's less than 4, but that's okay as long as it's at most 4. Since D is 4 and H is big O of log n. How long should searching in a 2-4 tree take? So searching in a 2-4 tree takes big O of log n time. Yes. So we got our logarithmic search times, just like what we had before, which is nice. So surprisingly, this is quite simple, right? So that brings me to talking about some operations we could do with 2-4 trees. Let's talk about how we would do an insertion into a 2-4 tree next. So before I gave you a general idea of how you can insert into a multi-way search tree, now I'm going to get more specific. So I'm going to insert like before. So I'm just going to use the algorithm that I described in high language terms. I'm going to give you pseudocode in a bit. I'm just going to insert like before. However, remember I gave you that case where I talked about the whole idea that the tree's nodes could get really, really fat? We have a size property at our disposal here. So I want to make sure that the nodes don't get too fat. We want to take care of our nodes. Our tree is very diligent like that. It's very self-conscious. I feel bad for the tree sometimes, but that's okay. The tree can live its life like anybody else. So, what do I do? So, insert like before, but notice that a 5 node, so that's a node with 5 children, would violate the size property, right? So when does that happen? When can I possibly get the node where it gets too wide? When it gets too fat? What happens? That's when I put something into what was already a 4 node, right? So it is possible for a 4 node to become a 5 node, causing we're going to call causing an overflow. So this is the muffin top of tree situations, okay? So, that being said, I have an overflow. So, to fix this, so if this ever happens, this overflow happens, to fix this, we use a split operation. So, we use a split operation. So it's called split. And I'm going to draw a picture for you. That should hopefully help explain it. I put more details in the notes. So you got to imagine you at some node that has an overflow that just happened. So that's the node for which you perform the insertion at. So call it node V, for example. So it has a parent, U. And then it might potentially have some keys up here. But the point is it's just the parent of this node. So this is the node that has the the overflow occur at. For simplicity, I'm drawing leaf nodes, but they do not need to be leaf nodes. These can all technically be internal nodes. So I'm going to label them as C1, C2, C3, C4, and C5. So I have K1, K2, K3, and K4. These are the keys of my 5 node. So I perform the insertion, I get a 5 node. This causes the overflow. This means that I need to do something with this. Here's how you can look at this. Here we go. So I'm going to use a different marker to indicate this. I'm going to use a green marker. So what you want to do is you want to find a place roughly about the middle. So by convention, I normally pick to the right of the middle if ever I have to make a tie between two. Normally it's a good idea to just pick one as a convention. I normally pick the right, and whenever we do anything, we'll assume it's always to the right of the middle. So what we do is we're going to pick about the middle, right about like that. And what we're going to do, so I'm going to refer to this key or the record associated with that as V. Now, before I talk about the node being V, don't be confused. This is not that. What I'm going to do is I'm going to move V up to its parent. And then what's going to happen is very simple. I'm just going to split this node into 2 nodes, for which these are now going to be children of V. So the record V, those will be the one with respect to the left and to the respective right. So let me draw the picture of what this looks like now. So you move that up. So you move V up to the parent, and you split this into 2 smaller nodes. So now K3 goes up here. And to its left, we're going to have a 3 node. And we're going to have a 2 node here. And let me label these. So this would be C1, that's C2, this is C3, this is C4, and this is C5. Does everybody see that? So I've moved 3 up here, and then I split it into 2, and now that becomes the left and the right of K3. So whatever the record is here, this would become the technical child in the location. This would be the one just before it. Okay? So you might naturally ask, well, Dan, does that mess up anything in the parent? The answer is, of course, no. Because notice that this originally has 2 keys off to its left and its right. So what happens is, all this one would do is come up here, which those would be in the original left and right keys here. All I would do is put this in there and I jam those in between. So now it's not going to change any of the ordering that we had and our property should be maintained. So this is called a split operation. Now, I must stress that this can happen multiple times in the tree. So I'm going to say multiple overflows can occur. So here's how the put is going to work. We're just going to simply go from the insertion point up, and whenever we have to do a split, we perform a split. This pushes up a record. This potentially could cause the tree to grow up like a flower. So I want you to think about a whole bunch of seeds in the ground growing out of the ground, working their way up as one singular flower where the root is growing upwards. So this isn't where, so the best way you can imagine this is not really like that's going down, because the level of all the leaf nodes is all the same, right? So it's going to only go up. Does everybody get that? So these splits are going to cause the tree to go up as this occurs. So let me do an example with you. So let me draw out a tree for you. Okay, so here's the tree I had before. Now what we're going to do is I'm going to perform some insertions. In particular, I'm going to do one insertion here. I'm going to insert 29 into this tree. Where should it go? So what did I do before? I used get to find the node, which is the lowest insertion internal node. Remember? I go all the way down where it should be, right? Where should Z be? So where should I end up being? So like Z is right here. So the lowest insertion internal node should be this one right here, right? So that's where I'm going to insert 29 in. So it gets inserted into here. So I shuffle everything over. So don't remember, all these get shifted around with it. And then I put in 29 right here, 30, 36, and 42. Is this okay? Is V okay here? No, right? This is causing an overflow. This is overflowing. Can you see that? We're having a muffin top situation. We need to deal with this. Okay? So, what do? I move. What do? What's the split? Remember, I pick right about the middle. If I need to make a tie, I kind of do something like this, right? So what am I going to do? I'm going to move up. Which thing? I'm going to move 36 up to the parent. And I'm going to split this into two smaller nodes. So let's fix that. So 36 goes up. And then now I have to split this into two nodes. I need you to make sure you realize that I'm not losing anything by doing this, okay? So this leaf node is now staying over here with this node. This 36 no longer exists, right? It's up there. Remember, that's the record with keys 36. And then this goes to the left of it, that goes to the right of it. Am I done here? No, right? This overflows too. So what should I do? What should I do? I need to perform a split operation again. Remember? So I cut right about the middle there. Pick to the right. I'm going to push 28 up to the root. Now, do I even have a root anymore if I'm going up? I'm going to have to reassign a new node and call that the root. So now that's 28 here. And now I've split this to 2. So now I have 11 and 21. And on its right, I should have 36. And then what? What's the left of 36? It should be 29, 30, just like we had before. What else? Then we have 42 on this right side. On the left side, we just simply have 5 and 7, the leaf nodes. 5 and 7. And we have 18. 18. And lastly, over here, we have 23. Apologize, the 23 melted in the microwave, okay? So as a result, am I done? So remember, this is working its way up from V. So when I finish the split, I check this one, then I go up the tree, just checking if any violations occur where this overflow happens. If the overflow does not happen anymore, we're done. So I don't have to go all the way up the tree. I just have to stop wherever the overflow keeps on happening. Because remember, before that happened, an overflow wasn't there, right? So the preconditions will meet the postconditions and we're okay. So anyways, next day I'll show you the pseudocode. We'll do the analysis and then we'll move on to removals. And it's worth noting that I put more examples of this in the notes. So should you be interested in that? So I give a couple more examples of how to do this. So next day we'll come back to more on 2-4 trees and possibly the very final thing we'll talk about in the main topics here. So I say thank you very much and have yourself a beautiful day.